Hey guys, and welcome back. We're going to start off about where we left off. And so we were looking at this cancerous mass last time. So as we were looking at that cancerous mass, we were seeing that it's, one of the things like right here, that medical diagnostics. So you can look at disorders as well as diagnosis by using things like these radioactive isotopes. It's also used for other things like fossil dating, as we kind of mentioned, half life. And we're not really getting into that right now, but it's something that can be used with radioactive isotopes. So here we have the guy's thyroid, and we can see the phosphorescence of this in this image of this MRI as we're looking at, and can see the diagnostics. And this is a result of tumors. They're going to be heavy on the use of resources. And as they are using a large amount of resources, if you use like a radioactive isotope, this isotope is going to accumulate there, not because it wants to or because it's just magnetized to go there. It's nothing to do with that. Instead, it's really all about that. It's just using heavy resources. So the resources being used include those radioactive isotopes that are going to accumulate, and then it's going to be something that's going to show different on an MRI, like we see in this instance. So, with energy, energy is the capacity to do work, to cause change. There are two different forms of energy, and that's going to be potential energy as well as kinetic energy. So, potential energy, this is the energy that is stored. And let's say that I'm climbing a ladder of a high dive. With each rung of the ladder that I progress, I am increasing my amount of potential energy. So I will climb and we'll have rung after rung after rung, and I'm going to increase my potential energy. If I get to the very top, right before I jump off, I'm at the highest point of potential energy. So as I fall off the diving board, I've now converted that potential energy into kinetic energy. So kinetic energy is the energy of motion. If you think of a roller coaster that's moving up, this is potential energy. Whenever we finally crest and go down, that is the kinetic energy. So kinetic energy is the energy of motion, and potential energy is going to be the energy of essentially stored along the way. So with electrons, electrons are going to have potential energy due to their distance from the nucleus. So, as a result of this, you're going to see the way an atom will react is really due to the electrons in the outer shell. So, the electron shells, if you looked at an atom and you're looking at the different rings, the valence rings, you're going to find that the first ring is going to contain a max of 2 electrons. The next outer shell has a max of 8 electrons. This is something that you've probably covered before in Chemistry 1. So, with each increasing shell, increases the distance from the nucleus. And so, we're going to have uh, energy affected as a result of that. So, if you looked at this is the closest to the actual nucleus, and you can see as it progresses outward, we can see energy absorbed as it is essentially moving down. So, the highest energy level is going to be this third shell shown in this um, image here. So, chemical behavior of the atoms is going to be determined by the distributions of the electrons in electron shells. So, the outer shell is the shell that is really important on determining how the atom will act and react. So, the periodic table of elements is going to show the electron distribution for each element. So, here we have that just a really simplified part of the periodic table. And you can see hydrogen on the upper left. And you notice that there is 1 electron in the outer shell. And if you go to the other side, you can see 2 electrons in the outer shell. In the first ring, this outer shell, you can see that that first ring has a max of 2, meaning that helium is going to be full with just 2 electrons. As you get into other things like this, you start to see an increase. So there's 2, there's 3, and you can eventually go to neon where we have 8 electrons in the outer shell. This outer shell is full. The elements that are in this column, the 8th column, are going to be called noble gases. And they're noble gases because They're all gases, and they don't react with other chemicals easily because their outer shell is full. So if that outer shell is full, it's going to affect their reactivity. As a result of their inability to react with things, it's going to cause them to typically be loners. They're not going to be interacting and reacting. So we can look at some of the naming of the periodic elements and part of how to read the periodic table. Once again, this is review and something you probably already know. If it's not, make sure you really brush up. By now, you should have picked up your textbook from the office. So make sure that you do that if you haven't already. It is just really important that you have that. So at the very top, we have the atomic number. The atomic number is going to tell you the number of protons that this atom has. Protons plus neutrons will give you the atomic mass. And so if you look down at the bottom, you have the atomic mass. This is how much mass this actually takes up. So we have the protons and the neutrons making the atomic mass. Notice that the symbol here is helium, H, then little e, and it does matter with the capital letter always for the first one, and the second letter is always lowercase. This is something that somehow missed out when I was in high school, and when I was in college, I learned it in my first early part of my first class, and I still remember that painful time. Okay, so we show the electron distribution to the right. If it's going to have two protons, and it's not an ion, then it's going to have two electrons too, because the number of protons, the positives, are going to be the same as the number of electrons, which are the negatives. As a result, it's going to have two protons, two electrons, and this one, so 2 plus something gives you 4 for the atomic mass. That's obviously 2, so it has two neutrons as well. As we start looking at the first shells, as we talked about, one electron in the outer shell for hydrogen, it needs another electron to be stable. So oftentimes you'll see hydrogen that's either H2, meaning that's bonded to itself because it's sharing, or you can see it easily bond to a lot of different a lot of different atoms are going to have hydrogen bonded to it. And so if you look, let's say methane, CH4, has 4 different hydrogen bonded to that central carbon. Here we have helium. Its outer ring is full, so it's not very reactive. Here are some other things. We have lithium with 1. We have sodium with 1. So this column is going to be highly reactive with things in the 7th column. And we'll talk about how it's going to become a cation and an anion as a result of this column 1 and column 7 leading to ionic bonds. We'll get to that in just a moment. This is pursuing on, keep going down. We talk about oxygen a lot in this course, and so here's just a view of oxygen. Notice that has 2 electrons there in the outer shell, 2 electrons here in the outer shell, and then a random 1 and a 1. This kind of place where we have an unequal distribution, that's going to be very important a little bit. So these valence shells are going to be occupied with these valence electrons. And once again, electron and a valence electron, the valence electron is just kind of pinpointing where it's located. It is the electron. It is the thing that we're talking about. But it's a really specific way of identifying it. So we know that it's referring to the shells, the electron shells. So let's start talking about the way these are going to interact. And we're going to do this with bonding. So chemicals are going to bond, and the most common chemical bonds we're going to talk about are covalent bonds, ionic bonds, as well as hydrogen bonds. Now, you have a worksheet that I shared with you last class, and it has the markings for the different kinds of bonds. You already should have completed the areas that shows the atom, the valence electrons, molecules, I think, are some of the different points. And if you're forgetting what it looks a lot like this. And you can see that we're going to be talking about stuff on this side, which is going to include the atoms, molecules, valence electrons, and then we're going to have bonds, which are going to include the definition, a picture that you're going to draw. And it doesn't have to match exactly what I put on the screen, but I want you to put together an image and then other information that you can gather about that. And so that's going to be seen for ionic bonds, covalent bonds, and as well as electronegativity as we start to get to that. Okay, so covalent bond. To me, when we're talking about covalent bonds, a lot of times I think about relationships. And people oftentimes have this perfect ideal of a relationship that you are incomplete without the other individual, but together you are so much stronger and better. Well, covalent bond has that definition of it's going to share electrons. And as a result of sharing electrons, it's going to be stronger. And by the way, this is the strongest bond. And it does this by fulfilling the needs of the other atom. So if one is short 2 electrons and the other one is short 6 electrons, if those two things bond together, they're able to create this bond that allows the sharing of those electrons. So the electrons, as they're going to be circling that atom, can also circle around the other atom. And as they're moving, they're going to satisfy what's called the octet rule. And so it's allowing this atom to be completely satisfied and this one completely satisfied. And they do this by sharing that 8 because the electrons move at such a fast rate that essentially it is taking care of the needs of both by that sharing. So, as you would guess, this is going to be the strongest type of bonds, and it is a covalent bond. So, in covalent bonds, you have two things, and we have hydrogen here. Remember, the hydrogen is showing just the proton there, the positive, because once again, we know that it lacks a neutron. Notice that we have this kind of affinity. Do you see this drawing, this peak nearing each other? And here we have H2. And it makes sense why we would have H2. And that's because we have 1 electron in the outer shell of this hydrogen. That result, it needs 2. So if they share, then they can then have 2 as they're going to be sharing around each other, fulfilling their octet rule of their outer electron ring need. So we can see that the example is the single bond that we have here, H to H, and we will write this as H2. So it is abbreviated, but this is showing that there is a bond and it is a single bond. There are other kinds of bonds like double bonds or triple bonds. And here's an example of a double bond below. This double bond is something that it occurs absolutely. It is really common. And it is a very strong bond, but it's not really what we want to focus on in biology. So this is kind of leading to our understanding of biomolecules. It is important, but going into triple bonds and all those things, we may mention it throughout the course, but it's not going to be labored on. Here's some different structures showing the electron distribution that we have here. And here we have kind of a model showing that. I don't know why this is over here, but we can see that we have the sharing. And this is what I want to come back to. And this is going to be a point that we focus on for an entire chapter, is the way water works. So H2O, we can see that there is 6 electrons naturally in its outer ring. And so hydrogen is bringing 1, and the other hydrogen is bringing 1. As a result, it gives it the 8 for the octet rule. And notice this, we have hydrogen here, and all this area is going to be oxygen, shown in red. This has an unequal distribution of the electron cloud. So that unequal distribution is going to have the electrons, which are going to go around this, and we have several around the oxygen, but then it's going to go far out around each hydrogen. Since it's spreading out the negativity here, and it's concentrating the negativity here, this area of oxygen is going to be more negative compared to this region. Since that's the case, you're going to have this have a negative charge here and a positive charge by default. By comparison, it is more positive than the other side. Even though you may be argumentatively looking at it and say like, hey, this is negative and this is also negative. But I would just use it as a comparison. Which side is more negative? And you would then tell me, and so I would then point out that this side is less negative. So it is marked as a positive, even though we know that. So, due to that characteristic, water is going to be attracted to other polar molecules like water. Water is so small. And I mentioned this in lecture today in class, and that is to give you an idea of the size of water. You can put in a 5-gallon bucket of water. There are more water molecules than 5-gallon buckets of water in the Atlantic Ocean. So, once again, there are more water molecules in a 5-gallon bucket of water than 5-gallon buckets of water in the Atlantic Ocean. Just to kind of give you a scale of how small water is. So, we'll look at water, and in our future chapters, we'll see it again and again. But one of the chapters is really going to focus on it and how it's going to have certain characteristics. So, it will be well revisited. And we'll look at it in just a moment, too, with polar and nonpolar covalence. At the bottom, we can see methane. And so methane is going to have an equal distribution of all of those bonds. So we have C, and it's going to have 4 electrons in its outer shell. And those electrons you can see equally distributed around that carbon. And we have 4 different hydrogens that are going to be bonding to each side of this, making it a completely balanced compound. Notice its equal distribution. Now take a look at water's distribution, the one above it. Water is going to have a side that's more negative than the other. As a result, it's going to have a negative pole and a positive pole. By definition, it is called a polar molecule as a result of that unequal distribution. So water is a polar molecule because of the unequal distribution of electrons. We look at methane, and it has completely equal distribution. That is nonpolar. Both of them are covalent, but one is a polar covalent, one is a nonpolar covalent. So as we look at that, we'll look at essentially that we have unequal distribution versus equal distribution. And that is the difference between polar covalent and unpolar covalent or nonpolar covalent. So it's about the unequal sharing. So here we have hydrogen, and we see that there's 1 electron there. And here we have this charge. And notice this kind of weird symbol. That is the symbol that they use to represent charge, and it's just universal in science. And it's from the Greek alphabet. So you have a negative side, and this side is going to be positive as well as this side. As a result, other water molecules are going to be attracted to the corresponding, so negative to a positive and the positive to a negative. And water is going to form a network with other water molecules. That network is going to cause it to have a certain strength. And we'll mention that in a little bit as we talk about polar interactions. Now with ionic bonds are going to be formed from ions. And it seems like it's just an obvious, but you take something, let's say, that's in column 1. Column 1 has 1 electron in its outer shell, but if you look at the shell underneath it, that shell underneath it is full. And so obviously it would have something like 8 electrons in its outer shell. If it could just get rid of 1 electron, it would have a completely stable outer shell. So to fix this, the atom will get rid of one of the electrons. Now, since electrons are going to be negatively charged, you're going to get rid of a negative. If you get rid of a negative, you're going to mark it as a positive. So something that has got rid of a negative charge is marked as a positive ion. These ions are called cations. So it is an ion that has a positive charge. So as we look at ions, we're going to see some that are going to get rid of an electron. You're going to see some that have 7 electrons in its outer shell, that if it could just get 1 more electron, it would be very stable. And you're going to see them accept an electron. And you're going to see those have a negative charge as marking them as an ion. And this is going to make them an anion. So a characteristic of ions is that we have cations that are attracted to anions. And here we have sodium and chloride. We have sodium, which we see with this electron that's just one too many, and it gets rid of this. And we have chlorine that's going to accept it, and that's going to give it its complete octet 8. It's happy, and sodium is happy, but then something occurs. Due to one being a cation and one being an anion, this opposite charge is going to cause them to be attracted to one another. So that attraction, one to the other, is going to cause them to bond together. Since they are bonding together, this is a bond, and it's an okay middle of the range strength bond. So it is a bond, it has strength, but here's the thing. Since it's based just on attraction, it is not a really strong bond. If you think of the typical kind of reaction where you have it based on just attraction, just like in a relationship, something that's based on just attraction is not going to be a strong relationship. So this chemical relationship is going to be a weaker side, middle of the road type of bond. It's not near as strong as the one that is a covalent bond. Covalent bonds are very strong. Ionic bonds, they're middle of the road in strength. But when you get to other things like hydrogen bonds, those are very weak. We'll talk about those in just a moment. So as we identified, just to review a little bit, we have the cation, which is going to be the one that has the positive charge because it lost a negative. And then you have the anion, which is going to be negative because it gained an electron, so it is more negative. So we've identified a cation, we've identified an anion, and we identify that both of those ions are going to bond together. That's going to make that ionic bond. So ionic bonds are going to be called ionic compounds, and many of these are just referred to as salts. Like you take your sodium chloride. This is an example of just normal table salt that we see. That's an example of that column 1 and a column 7. And if you look at a column 1, column 7, those combinations, they go really well together of giving and receiving of electron, and then they're going to be attracted to each other because of their charge. So oftentimes you have a lattice structure that's going to occur with sodium chloride, and you have this kind of stacking and this crystalline form. If you look at the structure on the left, and even looked at it with microscopy, you're going to find that it's going to be very straight ridges, and it is due to this lattice structure that you have based on these sodium chlorides that are going to be stacking together. So the weakest chemical bond that we're going to talk about is going to be hydrogen bonds, and these are going to be with van der Waals interactions. So a hydrogen bond is going to be basically the attraction of one side to the other side. So think of the water, the polar interaction that we identified. So water is going to have this negative side, and it's also going to have another water molecule that's going to have a positive side. Those sides are going to be connected, and they're going to be not deeply connected or interlocked or interwoven or just stuck to each other. Instead, it's going to be an affinity. It's going to be drawing it to the other. And as a result of that drawing together, it's going to have some strength. So hydrogen bond is going to be strong in the sense of just a bond. It's going to be strong because of that attraction. If you're trying to classify hydrogen bonds as in strength, this is the weakest type of bond. You're going to see hydrogen bonds again whenever we look at DNA. And this is going to be several units away from now. But when we're looking at DNA, at the very center part, you have the nucleotides that are going to be in a long chain. You're going to have another nucleotide that's going to be in a long chain. As those are going to be bonded together with the base part facing the base, the purine bonded to the pyrimidine, this is going to be connected through hydrogen bonds. So those hydrogen bonds are going to be drawing each other. Think of a magnet. You can break the magnetic pull, but it can also be held together. It's going to have a kind of an inherent nature to bond together. So that characteristic gives strength to these. So oftentimes I say that DNA's weakness, being its hydrogen bond, is its strength, because when you separate it, it's going to separate at those bases, which is going to leave a template for other nucleotides to pair. And it's the correct nucleotide, since it's revealing the part that's differentiated, being the base part of each of those nucleotides in the DNA chain. So hydrogen bonds, they are definitely a big part of our understanding of biological science. So a couple things here as we look through and get ready to end our session, and that is we can see some of these hydrogen bond interactions. So this is the positive side of water, and this is the negative side of ammonia, NH3. And I know we haven't really talked about ammonia, but we can see the unequal distribution, and we have the high amount of negativity on one end and the amount of positivity on the other end. These two are going to bond together as a result of those characteristics. This is going to cause water and ammonia to bond together and have a certain strength. All right, guys. So this is where we're going to stop for today. Thank you for tuning in and staying with us throughout. I know it's long, I know it's lengthy, but we're making the best that we can through the situation. And I look forward to hearing from you. Definitely keep taking your notes. When you get to a certain point in your notes, make sure that you are taking pictures. And something I would like for you to do is stop in your notes and summarize. Make sure that you're drawing, not just drawing things that you see from the book, but think about it. And in your notes, as you're taking your notes, put little questions to the sides. Make sure you're doing these things, because I want you to be a great student. You're in an upper level course, and things that you do in an upper level course is you need to go above and beyond, and just making sure that you're an excellent student. So it's great to see you, and I look forward to seeing you soon.